Good morning, warm welcome from my side. Hi, I'm Henning. Welcome to the third day of the Azure Data Explorer Level 300 workshop. We had already two really exciting days. Had the pleasure to listen to Odette, to Svea, to Slavik, and yesterday the hands-on lab with myself. And today I'm super thrilled to announce three great talks, and we're going to start with Vincent Philippe talking about time series and machine learning, process mining using ADX. The second talk is going to be held by Avner, focusing on optimizing for high concurrency applications using ADX. And last but not least, very important, visualization using Power BI and Graphana. And by that, I would like to directly hand over to Vincent Philippe. Take it away.
Thank you, Avner. I'm trying to share my screen right now. Oh, okay, I have to bump you out. Let me know if you can see my screen.
Perfect.
Alrighty. So, hi, my name is Vincent Philippe Lauzon. You can call me Vincent. I'm a product manager with a Custo team, and today I'm going to talk to you about time series and advanced analytics. The topics we're going to cover today in order of, well, chronologically, but also of importance. So might not have time to cover everything, but we'll make sure that we cover at least the first two, time series analysis. So things like anomaly detection and forecasting, and clustering plugins, so a bit of a adventure in the ML territory. Then if we have time, we're going to look at scan operator, which is a new thing for process mining and sequence analysis. And finally, extensibility with Python inside the KQL queries. Of course, if you have any questions, feel free to use the chat and my colleagues will answer or will stop me so that we can discuss them live. Without further ado, let's start with time series. So time series analysis, it starts with the make series operator that kind of generates the time series. And we have a bunch of functions specialized for it, doing stuff like filtering, statistics, regressions, and all that good stuff. But I think talking about it won't get us very far. So let me share my screen and I'm going to show you how it is done. So you should see my KQL editor screen. By the way, I just found that out this morning. If you want to rename those tabs over here, this is the syntax you should use. A little pro tip for you. But let's start over here. So we're going to look at some data, and I'm going to try to show you what the time series is. So usually when we look at data, very often it has timestamps on it. So we can say that it is a time series. If I look at this table, for instance, you can see there's a timestamp on it. So that's a history of basically clickstream history. So you can see that there's a timestamp, there's different information, the browser version, the OS version, the country of origin of the person that was clicking on whatever website where that was recorded. So you could argue that that's a time series because it has a timestamp on it. Another way to do it would be, let me just copy that so it's a bit faster, would be to use summarize. So we can say summarize count by bin of timestamp, let's say 1 hour. Instead of taking 100, I'm going to render it into a time chart. So if I do that, yeah, we have a time series, and that's basically the story of the click stream. You can see that it goes up and down during a day and probably even the weeks. And a different way I could do that is using that make series operator. So this is where we're going to start to talk about time series. So here I'm going to say make series count. So still using an aggregation operator. And then I'm going to say on timestamp and a step of 1 hour. So it's kind of similar, and it does give exactly the same result. So what is the difference between those two? Why did I bother introducing a new operator? Let me show that. So if we look at this one, if I recall it, and you look at the underlying table, that's what it's doing. You probably know, if you've done the workshop yesterday, you probably know that aggregation summarizes kind of a group by in SQL and gives us a table with counts and time stream, basically bucketing the times in 1 hour buckets and giving me a count. So this thing, if we look at it, if we look at the underlying, it is different. So what happened here, this is what we call a time series in Custos. It's an array or a vector or a list or whatever you want to call it. It's basically packing a bunch of numbers inside the same value. And if we look at that, actually, if I comment that out, and if I look at the output schema of that query, you'll see that the timestamp is a dynamic and the count is a dynamic because they're both arrays, basically. So if we come back here, you can see that, yeah, so I got a count array with different numbers, and I got a timestamp array with different string encoding the timestamp. So why is that useful? You're going to see that we have a bunch of operators that operate on those time series. So now you can consider those arrays as time series. So one of the interesting things we could do, if I uncomment that and I go back here, so I got my time series, I could partition it by OS version. And now I got a 3 time series. I partitioned by OS, so this is an old time set data set. So I don't have Windows 11 in there, but basically you can see that it split the different time series. So now I can start to do something interesting with that. If I would show you with a different browser version. So browser version, there's a lot of them. And if we look at it, at some point, you'll see that the UI will say that's a maximum of 100. You want to bypass the limit. So we're brave, so we're going to bypass that. And we get a graph that doesn't tell us much because it's way too busy. There's way too much curves in it because there's 114 records. So just keep that in mind. I'll come back to that. How we're going to analyze a lot of time series. 100 is not a lot, like we're going to analyze in the thousands, but just keep that in mind. I'll come back to it. So what I could do with that, let me copy that. Something interesting I could do with those things. I could, first I'll give it a name. I'll give this column a name. Call it cardinality, so I can refer to it instead of count on the score. I will partition it by OS version, and I'll do. Let me actually copy that. It's going to be faster than watching me typing. So what I do here is I extend. I do computer stats. So get specialized functions for computing stuff over a time series. In this case, I'm using the one that computes the stats, and I'm extracting the minimum, maximum, and average from it, and basically displaying it so for each partition, so for each OS version in this case. If we look, if I go down here, you'll see that the statistic column actually contains a bunch of things. Including the minimum, maximum. So you see it includes the minimum for the value that I aggregated over here, but also includes the first point exhibiting that value. So sometimes it's useful to know that. And maximum, same thing. Average, maximum IDX, etc., etc. Standard deviation, variance, and the length of the array. The interesting thing about that is that it computes it on every time series. So if I had thousands of time series, it could compute it very fast. So it's optimized to compute on multiple time series. Now let's look at the different data set. Let's look at the demo series 1 and render it as a line chart. So here we have a data set that you can see that is kind of a bit noisy at the bottom and then kind of grow up. And this is typical if you've done IoT, like a runaway sensor, basically. You have a sensor that kind of could be temperature, so it takes the ambient temperature for a while, and at some point it just goes wild and it goes up. So it could be interesting to detect those. And so let me just show you the documentation all the functions that we have to address time series. So that's the ADX documentation. If you search for time series, you'll have a time series. That's not the right link. There's two time series links. Analysis overview. So you'll have a little overview over here, and then you have all the functions that we could use. So there's a bunch of functions that just apply function, like applying a sinus or cosinus on the time series. Decompose, we're going to look at it. Fast Fourier transform, filling forward and backward, filling linear. We're going to look at some line fitting. So there's a bunch of functions we can use. I'm just going to show you a couple of those. My goal here is just to sort of pique your curiosity so that you might think about a scenario with some customers, and then you can go into documentation. But here, what I'm going to do is I'm going to try to detect that point, or try to think about if I would have those sensors and I would like to be able to pick the sensor that does this runaway thing, how would I go about doing it? So a way I could do that is to do an extent, and I'm going to do a fit linear. So here I'm going to do series, fit linear. So if you're familiar with linear regression, that's exactly what that is. Actually, I'm going to use the dynamic version of that. Fit linear dynamic. And I'm going to do that on Y, which is the only column that I got in this time series. And I'm going to extract the line fit. You need to look at the doc to find that out. But basically, if we look at that, I have my underlying curve, which is the Y thing, so that we looked before. And then I got the linear regression on top of it. Linear regression, if you're not familiar with that, basically you take a line and you try to fit the curve underneath as best as you can. And of course, this is not a line, so it's hard to do it. So here I kind of detect, if I would look at the slope of the line, I could tell, okay, the sensor reading is quite increasing during the time period, but it doesn't tell me anything about the breaking point. So something quite easy I could do is just use the linear line 2 version, which of course I mistyped. Sorry, it's 2 lines. There you go. All right. Now it does, if you just look at the fitting, it does basically 2 linear regression, and it finds the best breaking point. So that's very useful for that type of scenarios. And you can imagine that we could run that on thousands of time series, and we're going to do an exercise like that a little bit later. So let me continue. Here I'm going to do some filtering. So I've showed you linear regression. Now I'm going to show you fear, the fear function. So not fear, but fear, finite and false response. So basically passing a filter over your function. So if I take the same series and I apply a filter, so you see that's my underlying curve, and this is the, this is the filter curve. So you see it's a bit filtered. And if I add a couple of one here, you see that it becomes more and more smooth. So what that is doing, basically, this is the filter I'm passing, 1, so it's basically taking a window and passing it over the function. So if you would like to calculate it yourself, you would take the first point, adding the second point, divided by 2, because you take the average, and that would be the first point of the smooth curve. And you do that again for the second and third point, third and fourth point, etc., etc. So the reason it's smoother when I do a bigger filter is that I basically average out on more and more points over my curve. So that, again, that can be useful if you know that you have a lot of noise in your sensor reading or whatever data that you have. It'd be useful to do a filter like that. There's a bunch of things you can do with fear. It's a very versatile tool. You can do things like doing difference equations, not differential, but difference. Like you could basically calculate the difference between a point and the last point. So computing the speed, for instance, if you have the position of something, you can compute the speed, instant speed on every point in time. So that can be super useful. If I'm coming back to the first data set, let me drop that here. So basically doing the same thing, partitioning by OS version. I just introduced a parameter DT, or delta time, 1 hour. what I'm going to do is I'm going to want to try to detect the seasonality of that thing. For that, I'm going to use another query. So let me type it in and explain it to you. So I get the same query here, the doing a count on timestamp over the entire time, partitioning it by OS version. Then I call the series period detection. That's another function. I pass it a few parameters. I say I want the period to be between 0 and 30 days. And I want 2 periods. So I want you to look at the data and give me 2 periods. And then I just extract. That gives me an array of periods, and I just extract the first one, the second one. And I just renormalize it because it's not giving it to me by time, but by number of points. I'm just putting that back in time, or in days, actually. And what it detects is for every partitions, I have 2 periods or 2 seasonality. I have 7 days and 1 day. So if you look back at the curve over here, you'll see that that's what we have. Like we have a period or a repetition, if you want, every day. If you look at the basically that fits into 1 day. And after 1 week, I got another repetition of about the same pattern. And Cousteau is able to detect that. So it's useful to, if you're looking at data and you try to find patterns in it, it's useful to look at the periodicity of your data. And now I'm going to look at decomposition. I'm going to paste the query and I'm going to explain you a bit the underlying model before we go into that. So here again, I'm using the same data set, partitioning over OS version. I'm going to select just one of them, the OS 10, so just this one. And I'm going to say series decompose. So decompose that series, that time series, into 4 components. In this case, the seasonality, trend, and residual and baseline. Before I do that, let me explain you what that means. If I go back to my presentation. So basically, it comes back to that equation. So you can take, here I'm going to talk about the model, and this is the only equation you're going to see. I won't go down a mathematical rabbit hole, just so that you understand what Cousteau is doing and what you can expect from when you do that. Because it seems very magical when we show that to customer, and when you think it's magical, you don't understand how it works, and you think it's beyond your comprehension, and then you have a bunch of expectations that might not be met. So I want to explain what it does exactly. So when you look at a signal and you have a model underneath, what you're basically doing, you're taking assumption about the data. A bit when you're doing a linear regression, for instance, you're assuming that your data fits on the line, and then you try to find the best line fitting your data. If that's not the case, if your data is like a bell, you know, we'll find a line that's completely meaningless. It's a bit the same thing here. So the model that we have for time series data, it's quite a common model. It's to have a trend, seasonality, and then noise. So what does that mean if I trace a time series on the graph? First, I have my trend. So my trend is, does the data generally, does it go up or down? Basically, that's the linear regression part of it. And actually, we use linear regression to calculate it. Then I take the same pattern with a given period of time, and I just repeat it. That's my other part of my model. I assume that my model, my underlying data is periodic, basically. So it does the same pattern, repeating over and over. And finally, I add some noise. So I assume that the data is not perfect and will have some noise. So there will be some repetition, but not exactly the same thing. So overall, it grows or it goes down. So that's the trend, then the repetition, and then the noise. So if we come back to the tool, now we'll be able to understand what it does. So what it does, if I look at my data, so that's my data set. And if we look at the trend is pretty flat, probably because there's only 2 repetition of that thing, but also you can see that there's not really a trend going up. So the trend is flat, so we don't learn anything there. The seasonality, so if I look at the seasonality, let me remove the trend. You can see it's pretty much the same curves, but not exactly. But if you look at it, if I remove the original curve, if you look at those things, you can see that on the right-hand side and the left-hand side, it's exactly a copy of the other. It's exactly the same spikes, and it's exactly the same trough. So it's the same, basically the same picture copy pasted, and that's the underlying model. The underlying model assumes that there's a pattern. It tries to find basically the average shape of the period, and then it repeats it, cuts and pastes it over time. And basically, if we add those together, that gives us the baseline. And the baseline is different from the real data because it's a model. And the difference between the real data and the model is what we call the residual, or what I call the noise. So it's basically the difference between the two curves. So you see it goes up and down. In this case, it's a pretty small residual, so it's good because it means that our model pretty much predicts the curve. But then what we can do with that, and what we do with different functions, is that we can look at the residual, and when the residual goes too high or too down, or the absolute value is too big, we can say, oh, that's an anomaly, and that's all we're going to do, anomaly detection. But it's done for you. I just wanted you to understand. So if I do an anomaly detections, I want to find anomalies in my data. I would type something like this. So again, looking at the same data. In this case, I just take the Windows 10 for ease of reading. And I use this time series decompose anomalies. I say find the anomalies and the value of the metric cardinality, and render it using an anomaly chart. And if we look at that again, if I remove this and I remove remove the anomalies. So again, those are my two curves. So the blue one is the real data. The orange one is my model. And the residual, we don't see it, but basically the distance between those two curves, this is where the anomalies are going to be detected. So it's quite interesting because when you show that to people the first time, if you don't show the baseline, you look at this curve and you say those points, those red dots are anomalies. If you look at it, there's not much reason to believe the curve doesn't seem to be going out of whack. It seems to be similar to the other one. So why are those anomalies? You need to understand the model underneath. So it's not magical. This is how we compute it, but it's super useful because you look at seasonal data and you're able to find anomalies in your data. So if you run a factory and you look at different sensors, you might be able to find some anomalies on your sensors. So it's a good tool to have in your tool belt. Very similar forecasting. So if I have a signal and I want to forecast in the future, how is it going to look? I can use this forecast function. I won't go into the detail, but basically here what I did, I kind of forced the time series to be longer than the data I had. So of course there's no data after the actual data, but the forecasting function returns the prediction according to the model in the past and in the future. So this is how it predicts the future should happen. And again, you can use that for forecasting your signal. Makes sense for everyone? Hope so. Let's look. And Henning, stop me if you see a bunch of questions I would beneficiate to discuss openly. We'll look at a different data set. We'll look at, I'll come back to that thing I told you about that could be useful to look at many time series at the same time. So I'm looking at a different data set. Here it's a data set from Azure SQL, where basically we're looking at the data reads per time per database, and we get like 3 columns basically identifying a database. I don't know that data. I just know that it's three keys that tell me about the data. So if I look at the table size, it's 2 million rows. So it's not a tiny table. It's not a huge table either, but there's 2 million rows. And if I look at the distinct value of those columns we looked at, so the lock, up, and DB, and I count those, it tells me there's just shy of 20,000 of those. So basically, we look at our original data set. There's 20,000 different combinations of those 3 columns. So if I would like to look at the time series for each database identified by location, I don't know what up means, I would have 20,000 of those. So you can imagine that that would be difficult to look at. And actually, what we could do is, yeah, that would be interesting. So let me show you two curves. And this is what I want to drive home and to land is, so this here, what I'm doing, I'm taking that signal or that table, and I'm averaging. In this case, I'm doing a sum. I could do an average. I would get pretty much the same picture. Over time, the timestamp column, taking step 1 hour. So basically, I'm bucketing every hour of time. I'm counting how many reads I have in each database, and I'm summing all those databases together. And it gives me this semi-flat signal. So you look at that and you say, okay, that's pretty average, nothing happening here. And that's kind of the danger when you look at average data, because you hide information because you sum things together. And I'll demonstrate that to you if we take a sample. So you remember that this guy over here is returning me one row per partition. In this case, I got only one partition, but what I'm going to do is I'm going to partition it. So lock up DB. So now I have 20,000 rows, and I'm going to sample just 5 of them. And that takes a bit more time. So you see that I have 4 curves that are at the complete bottom. If I remove the top one, this one. Yeah, so you see that the values are a bit different. So this is 5 samples that I'm picking up at random. The sample operator basically takes the 20,000 rows, choose 5 at random. It's not exactly random, but for a purpose it is. And if I take 5 others, you'll see I got different signals. If I take 5 others, I got quite different signals. So you see that the underlying data, each time series is very unique and different. But when you look at the average, you don't see any of that. So what can you do? You can look manually and visually at 20,000 of those curves and try to understand and make some deduction, or you can use time series analysis. That's what we're going to do. So an example, I'll just give you one example. So I want to find, let's say I want to find the curves that go down. Like basically, I want to find any signals going up and down, but I want to have something that has a trend going down. So I'm going to use linear regression, which we've used before. And that would tell me, for instance, that a database is unhealthy, for instance, because there's no read happening, or maybe it's not used or whatever, but something that I find useful to know. So yeah, I'm computing again the same time series over those 3 partitions. Here I'm just doing a filter for the arrays that have a length more than 10, because there's a bit of noise in the data. There's some time series there's very few points. So, and I'm doing a linear fit, so a linear regression. I'm catching the R-square, which is a statistical value, and the slope, so the inclination of the line. And I'm saying, give me the top 2 slopes by number. So basically, starting with the one that's most negative. And if I do that, and I compute over 20,000 time series, I get the result under 5 seconds, and I get those 2 signals going on. So I want you to imagine how much time that would have taken if we looked at each time series manually, and that's 20,000. But you might have, you could have a sensor farms of more than 20,000. You could have, many devices. It's kind of impossible at some point. So this is when you need tools to analyze that. I find that I call that finding the needle in the haystack. Basically, you want to find the time series that are interesting, and maybe you want to study those. Now that you found it, you know which one it is. You can look at the table. You know that it is those guys, and you can analyze those things to understand what happened these days. So to do root cause analysis, that would be quite a good tool. And that's what I had to say about time series. So do we have any question on that?
Just like a lot of people liking your session, VP. So great job, and they like the functions as well. I told them that we like them as well. And so yeah, please continue.
All right. So again, just advertising that there's much more functions than what I showed you. We looked at the decompose. Those are kind of divide and doing functions. Those are just run of the mill. This is useful doing fill backwards. So that's when you have sensors. Often you have a sensor that will emit data just once in a while, or maybe there's noise, or maybe there was like a network rupture, so you don't have data. So what you can do is linear interpolation. So basically, if you have 2 points separated by 5 minutes, you can fill it with different points. So that's a fill backward, fill forward. That's all what they do. Otherwise, there's different statistic stuff, person correlation. That's super interesting. So let me go back to my presentation. This screen. All right. So we saw that model. Now I'm going to talk about clustering plugins. So we talked about doing time series analysis and finding the root cause of some problems and doing some analysis. Now we're going to go a bit deeper with the clustering plugins, which allow you to find patterns inside your data. So the basic, if you've never done a bit of machine learning, that's also called unsupervised learning, because you don't give example to the system. Like a supervised learning, typical would be, I show you photos, you have to tell me if it's a boy or a girl, and I show you different examples, but I'll help you, I'll supervise you, so I'll tell you, this is a girl, this is a boy, this is a girl, this is a boy. You practice, now you tell me, is this a girl or a boy? So that's supervised learning. This is unsupervised learning. So this is my data. It's like your manager comes in on Monday. This is my data. Tell me what's going on, basically. And the clustering, the basic example is those dots. Like I got blue dots all over the screen, and I want to find clusters. And the system could tell me, hey, you got clusters over there. And they look like chocolate chip cookies from the Dr. Seuss universe, but it's purely coincidental. What's important here is that, so I'm doing clustering. This is a super easy example. We wouldn't do machine learning algorithms if we would just have those data, because with your eye, you could tell that there were 3 groups. Very often the data would overlap, so the system needs to take a good decision where to draw the boundary. The other thing is that our eyes are super good at finding patterns in a 2-dimensional picture. If I bring that to 10 dimensions, we're not so good at it. So that's where machine learning is super helpful, because we can find patterns in data. Sometimes not even continuous. You could have labels. Instead of having continuous data like that, you could have a column with strings, for instance. So your eyes is not too good. And I'll give you examples with some demos again. So coming back to this screen, so here we're going to look at a different data set. So demo clustering, I'm going to take 100 again, my lucky number this morning. So this is a list. Those are logs again. It works with logs. It works with any type of telemetry. I got a timestamp. This is a bunch of exceptions in Azure. I don't know exactly the data set. It's from some service in Azure. You can see there's a region. If you squint a little, you might recognize region. Like this is probably West Europe or something. North Carolina, I don't know what it is, but basically it's an Azure region, a scale unit of the service, and deployment ID. So they've got different columns there. So we're going to do some... we're going to look at the data, and we're going to try to do something, some analysis over it. So if I look at the data, again, I'm using this make series and just counting the number of events, the number of exceptions per slice of 10 minutes. So I look at that signal, and it tells me that it's going up and down. There's probably some seasonality. We won't look at that. It's probably 1 day. It is 1 day. But I see some spikes. And those are the spikes that I'm interested in. Why are they spikes during my day? Like I understand that it's going up, but it's really spiking at some point. So what's going on there exactly? So the first thing I'm going to do, I'm going to zoom. So you see that data over here, it's around 3 o'clock. So I'm going to basically just zoom in. I can't do that with the UI yet. I think it's coming, and if you wait a little, I think it's going to be part of Cousteau. You're going to be able to work with that timeline. But for now, I'm going to do it manually. So I'm defining a window of 4 hours around 15 o'clock, and basically doing that. And I see that I do have a spike over there. Okay. So now I want to understand what is that spike about. So one thing I could do, I could look at the raw data. I'll show you that just to show you how difficult that would be. So here I'm taking a window of 2 minutes around that point over there, and we're going to look at the data. And together we're going to try to figure out what's going on. So that's the name of the game. So we can scroll up, scroll down, we can even sort, and we have to find out what type of pattern do we see here? Do we see any repetitions? And then I don't know about you, but I don't see anything. We can try a bit longer. Maybe at some point, maybe you'll be like Cypher in the Matrix. You'll be able to see the code and to see the world as the code like Neo. But until then, we'll need some tool. So a tool that we're going to use is auto cluster. So I'm taking this 2 minutes, basically doing the same thing here. The only thing I'm adding is this evaluate auto clusters, and that's basically telling me. Telling Cousteau, look at the data and find some clusters in them. So comparing that, if we come back to my presentation, we look at the cookie dough. Here I kind of, I got patterns like this. Sometimes if you use algorithms like k-means, you have to specify the number of centroids or the number of patterns you're looking for. In this case, I didn't do that. I just said, auto cluster, find something. So that algorithm is smart enough to look at the data and find patterns and find the number of patterns it's looking for. So it does that automatically. So if we look at the first one, it's 50% of the data. So this is a big pattern. And what it finds is that there's no specific pattern for the timestamp. So it's not happening at one specific time. But it's happening in a specific region and a specific scale unit and a specific deployment ID, not a specific trace point. So that's what it's found as a pattern. So it says if you look at those columns and you equal that, you should find that it's 50% of your data. So that's interesting. So it would be something to look at. So you could look directly at your data and trying to find out what's going on. So that's much better than what we could do by just scrolling up and down. Another way we could do is trying. Whoops, that won't work actually. Let me find the entire query. So now I found that a pattern about the data that's misbehaving. Here, what I'm going to try to do is div patterns. So that's this function over here. That's a bit different. That's looking at anomaly data and at normal data and comparing them and telling me what is the difference between them. So it's a bit different. In machine learning, we call that the discrimination factor. So basically, it's the difference between saying that I don't know. I don't have a good example, but it's the difference between looking at, let's say, the champion at the Olympics, saying, yeah, they're all fit. So that's a characteristic that they all share. They all fit. They all train hard. And if you look at the Olympic champions and people in the street, and you say the difference is not only that they're not fit, but maybe they're in a certain category. Let's say for running, they're taller, or they're some of their bone of their body is bigger. So you learn more because you can discriminate between different types of data. That's what I'm doing here. So here, what I'm doing is I'm looking around 15 o'clock, and that's the the range of data of timeline that I'm looking at, but I'm also looking 10 minutes earlier. So that's going to be my baseline. And I define a column that's basically telling me if I'm looking at baseline or anomaly data. So if you look at that, I'm basically merging two bits of the timeline, and I have a column that's telling me which part of the timeline am I in. And then I'm calling div patterns with that columns and labeling it anomaly and baseline, which is basically the values that I define here. If I run that, so it's going to compare those 2 bits of the timeline. And again, it gives me the same thing, that it is those units that are the guilty parties, if you will. It looked at the data and it compared it. So not only it's a clustering pattern within the data, but if you compare it with normal data, like a baseline data, it is the big difference is that all the exceptions are coming from those guys. So in that case, it gives me like a confirmation. In the other case, it would give me something different. So in this case, it does tell me that. And what I can do then I'm going to do another query. So I'm going to look back at my data over 4 hours, and I'm going to basically define a segment. So I'm basically going to segregate the data. I'm going to look at the data that is from the specific region given by the pattern. So that was the region, that was the scale unit, and the deployment ID. And depending if it is that or not, I'm plotting it in 2 different curves. So you see that the rest of the data is behaving normally, and the spike is happening in my anomaly data. So I basically found the anomaly. I didn't find why, but I found that that's the data misbehaving. And for that specific data set, as you can imagine, that dates from a couple of years ago, but we talked to the team managing the service, and they found the problem was actually with that unit, because there was like a faulty software patch deployed back in the days. And so we did all that analysis without knowing anything about the data set. Like, we didn't know what the service was. We were not expert in the domain. We just looked at the data. And that's something you can do as well with your data. And that was the clusterings I wanted to talk about. Let me know if there's any questions in the room. Let me go back to my presentation. Want to eat cookie now. Scan operator. So that's a new thing we introduced. It's kind of the Uber for loop inside Custo. It's used to do process model, and used to do process mining, user analytics, funnel analytics. Basically anything that you can model with different states. So if you have a time series that goes into states that you can determine by rules, and you want to analyze that, you can do that with the scan operator. I'm going to show you a few examples. We're going to focus on the funnel analysis section. But first, I'm going to show you something a bit more mundane to introduce the concept. I don't think I have any slides after that. Yeah, good Python after that. Okay. So here I'm going to create data. So I'm not using a table. I'm using that operator. I don't know if you know that operator, range. So I'm saying range X, so I'm defining a column X from 1 to 10, step 1. So basically, for if you have done any programming in any language, basically for X equal 1 to 10 X plus plus. Here I'm doing an extent cum sum, so cumulative sum of row cum sum. So if you don't know that, if you know that function, you've probably suffered with it quite a bit. Actually, I think there's probably a twisted theorem you could do that everything you can do with scan, you could do with cumulative sum if you're insane enough to try. Basically, cum sum is doing cumulative sum of the row of the column here. So it starts with 1 because it started with 0. Then it's 1 plus 2, 3. Then it's 3 plus 3, 6, etc., etc. So that's a cumulative sum. Now I'm going to do that with scan, and it's going to look very similar. I'm just increasing not the difficulty, but the complexity, if you will. So here I'm doing a scan. So starting with the same data, 1 to 10. Then I say scan. I declare a local variable, or if you want, a column to the scan. That's called cum sum, cumulative sum. That is of type long, and I initialize it to 0. And I say we're going to go through a series of steps. There's only one step. As one condition to say that you enter that step. It's always true. So start simple. What we're going to do is that we're going to take that local variable that initialized to 0 and give it to X, the column X, which is 1 to 10, plus the cumulative sum. So I basically do the same thing, and I should have the same result. So at the end, I get this cumulative sum column over there. Now we're going to do something a bit more interesting now that we kind of understand the theory. And I warn you, scan it takes a bit of a while to get used to the way that we modelize the step. It takes a bit of practice. So here I got some data, some real data. Those are clickstream again. So I'm looking at user X that's been anonymized, going on some page, and the page has been given a pretty name so that we can understand what it is, product details, what have you, and a timeline. What would be interesting is doing some funnel analysis. So let's say that that's a e-commerce website. I would like to know what percentage of user went to the front page, what percentage of user went to the cart, did they abandon midway, that type of thing. So that's typical funnel analysis. For that, I'm going to type, I won't type it in front of you because that would be very long. My fat fingers, but let me make that a bit longer. So I'm doing a scan again. I'm doing a lot of things in that query. So let's break it down. So first, I'm filtering that data, saying I'm just interested in the page campaign landings. I want to analyze a specific campaign, product details for that campaign, add to cart, and purchase. So those are the only pages I'm interested in. Then I scan that. I'll come back to the partition in order. I scan that by doing 3 steps corresponding to each page. And I'm just putting constraint to enter the step. You need to be, for instance, to enter the second step, you need to be at 10 minutes from the first step. So we're looking at users that actually do a session, not that they come back the next day or something. So here we put different conditions to say that you enter step 2 and same thing. So 15 minutes after that and 15 minutes after that. And then we summarize the amount of user. Decount is kind of a faster way to do a count. Let's say it's count. Counting the number of users by step ID and page name. And that gives us the result, basically the funnel. So 15,000 users look at the campaign, 8,000 of them look at the product details, 400 went to the cart, and actually 16 just completed the purchase. And then you could ask the question, why does it go down drastically like that? Because they have to pay money, probably. If you want me to explain a couple of things, actually, I want to explain you. Partition is a super useful operator. Actually, that is kind of the for loop we have in Custo, and it doesn't look like that. Whenever you have time series and you want to split them and analyze them, especially if you want to sort them, partition is your friend. Because here what I'm doing is I say, take all the table that has a bunch of different user sessions, partition it by user. And then within that, those parentheses, those round parentheses, is a query. For each user, I have one of those query running. How it's implemented, that's a different story. Like Custo makes it efficient, but it is as if each query would be running on the set of users. So for each user, again, that's a for loop. So for each user, order the timestamp and then scan with each of the timestamp. And this is when it does this funnel analysis, basically. So even without the scan, that partition operator is super useful if you want to analyze different things, if you want to find the predecessor, like if you want to look at the time series and say what happened with the previous one, or if you want to fill value or go back in time, that type of thing, super useful to do partition because you don't want to have data from different assets or from different sensors, for instance. Anyway, so that's for the scan operator. And I have 10 minutes left, so I'm going to show you a bit of Python. Quickly, Python. Do I have something to say about Python? Yeah, so Python is the extensibility for Custo. Custo is great. We'll show you a bunch of functions, super powerful functions today, but of course, it's, you know, machine learning is a very vast territory or vast domain, and there's much more algorithms than we have encoded inside Custo. So instead of trying to keep up with all the libraries, what you could do is you could use Python. So that's talking about it from an angle of machine learning, but it's true in general. If you have an algorithm that you want to implement that doesn't make sense, like Custo is a functional language. If you have something that's more imperative, like you want to do step 1, step 2, step 3, and you know, like a typical C# or Python code, it's going to be very hard to do it. Very hard and sometimes impossible to do that in Custo. Then your kind of break out of jail card is to use Python. So you can use Python within your queries. We have a Python engine. That's an opt-in feature. So you need to say on your at the cluster level, I allow the Python engine to run. It's not more expensive. It's included in your cluster. It's just that it takes compute power. So it's an opt-in feature. The image is based on Anaconda 5.2.0, and we're going to bump that up in a few months. It executes on a single node by default, but you can also distribute the process, so you could fan it out. So it's super useful if you want to run an algorithm on a lot of data, because Python, instead of running on a Spark cluster that needs to download the data, like maybe terabytes of data, it runs on the same box than the data. And then you can fan it out where the data is, so it can be super efficient. You can install custom packages. For like a big use case is to do scoring with ML models. We don't recommend to do training because Custo doesn't support like GPU queues, for instance. So it's for a lot of reasons, it's a bit awkward to do training of machine learning models inside Custo. But scoring is definitely in the game. And don't think I have an example to show. Maybe I have an example to show it to you. But what you do is you train your model somewhere else, let's say in Spark, and then you score it inside Custo. So you could score, for instance, at ingestion time, you could score the data that you are ingesting using a specific model. Okay, so let's go back to demo mode. I'm going to show you something simple. I'm going to just show you how you call Python in Custo. So here I have some code, some Python code. I fence it inside those three ticks. That's basically a fancy way of doing a quote, and then you can put quotes within a quote, which is usually super annoying. You need to put backslash and stuff like that. So instead you put three ticks, and everything between the three ticks is escaped. And this is some Python code, so it takes arguments and does something, but let me go bottom up instead. So what I'm creating again that 1 to 10 table, and I'm evaluating. So plugin is something that you call with evaluate, and I'm calling Python in this case. I'm calling it on the specific code, and I'm passing an argument exp, so exponential in this case, or exponent of the value 4. And the expected schema for the output is, so Python is going to receive that table in input. It's going to convert it into a Panda data frame over here. But the output is going to have another column on top of what it already have, and it's going to be a column Y of type integer. And it's going to be already prepped in the Panda data frame here. So what I do here, if we go back to the Python code, I'm extracting the expression or the exp parameter or exponent, I said. So that's value. Basically, I'm extracting it from the dictionary because it's passed as a Python dictionary. I'm picking up the data frame, calling it result. Then I'm saying result column Y is equal to data frame column X. So I'm going to do like a batch operation, and I'm basically powering the column to the value of the exponent. So if I run that, I'll give you a bit more screen to see. If I run that, I got my column X, which is 1 to 10, and then it's 1 to the power of 4. 2 to the power of 4, 3 to the power of 4. It goes very fast, as you can see. Of course, this is an academic example, not super useful, but you see basically the drill of how you can pass code like that. Of course, this code, I could store it in a table, or I could store it somewhere else. I'm going to show you a model very quickly, because we're basically running out of time. But just to show you how you would do that. So in this case, I have a table called ML models, where I store different models. So that's what you need to do. You need to train your model somewhere outside Custo. And in this case, that table could have any schema, or you could bring the model in line. But basically what I did in the Spark notebook, I took the Python model and I pickled it. Pickling in Python is like serializing. It's like a serializing mechanism. So I basically took the object and pushed it into a stream of data, converted it to hexadecimal, and then I imported it inside. I pushed it inside the table. And that's what I'm doing here. I'm taking this occupation detection data, and I'm basically calling that function predict function library, which is defined over here, and that does the heavy lifting. Basically, it does the Python code of unpickling the model. So it takes the model and input and hexadecimal it and then load it and then does the prediction and push it. If I run that, I should have the prediction. And I think I do a summarization to get the kind of confusion matrix, basically taking, I didn't show you the data set, but basically it's supposed to predict true or false. So in this case, you see that if the data was supposed to be true and my prediction is true, I got 3,000 of those. If the data is false and my prediction was false, I got 9,000 of those. But I got some errors in my prediction, very few, because it's an easy to learn model. But basically it's just an example to show you that you can do that. You can actually bring machine learning models inside Custo, and you can use it. In this case, I'm using it in a query, but as I mentioned, very typical example would be to score your data as your data comes into Custo to basically enrich your data. And I'm done. So do we have any Q&A? We have 2 minutes for Q&A.
Oh, excellent. Thank you very much, VP. This was an amazing session. I, again, learned so much. And based on the questions, I also think the audience is quite interested. Now, some questions that I saw in the chat were, let's say, if I start more from the beginning, were related to, now that I have all of these beautiful functions to do anomaly detection, forecasting, and all of that, I guess I could also use those functions in dashboards, right, to visualize data.
Yep. Yeah, definitely. And there's actually a use case that we didn't talk about. If we go back to the beginning of the demonstration, where I was just using make series, I actually have a customer using that for dashboard. So a typical use case you have, or use case or issue that you have with dashboard, is that you have terabytes of data that you want to display on a screen that has only 600 pixels. So something very simple that you could do is do this make series and do maybe an average over each minute, and then you can display that. So then when you pass that to either Power BI or the ADX dashboard, you pass much less data. So you basically compress your data. So that's one example, but you could do linear interpolation and different things. So everything you can do in the queries here, you can do in the dashboard.
Yep, this is definitely, I can agree on that. Like, we see many customers that are truly successful with ADX. If they let the database do the job of doing all of the downsampling, using all of these great time series functions. And then, okay, maybe one last question. VP, please help me. Now that I can visualize all of this data, and I can visualize it efficiently using Power BI and dashboards, how do I trigger actions on this data?
How do you trigger actions?
Yes, let's say I find an anomaly and I would like to trigger an action based on that anomaly.
Okay, so yeah, we have a lot of customers doing that. Usually you trigger that from the outside. You would have something like a Logic app or Power app or something running in Kubernetes or something that probes your cluster and basically runs that query periodically, like every 5 minutes, every minute, every 30 seconds or whatever, and check for an anomaly and then does a trigger. So you could do that. Logic app is kind of my go-to for that type of action because it's quite easy to call Custo from Logic app, and then it's quite easy to raise alerts, so sending SMS or do whatever type of orchestration from Logic app. That would be my recommendation.
Great. Yeah. Thanks, Vincent. This was amazing. I think we can switch now to the next talk. Again, thank you very much.
Thank you, Avner. Thank you, everyone.
And with that, I would like to hand over to Avner. Avner, okay, please introduce yourself and take it away. Have fun.
My name is Avner Aroni, and I'm a program manager in the Custo team. I've been with the team for 7.5 years, working mostly on the engine side, but also on other aspects of the service. Here is Adx coming. I don't have a lot of time, and usually I give this talk over an hour, so I'll try to rush through that. The presentation is about how our customers are building high concurrency applications over Azure Data Explorer. From what I've seen, in many cases, Azure Data Explorer Custo provides now the best platform, I think, on Azure to build such an application. So I'm going to go over the use case and then the different features that we have to support it. Oh, okay, let's start. So let's continue to the next item, to the next slide. And I'm going to start with what is the use case, and it's going to start with a concrete customer which we worked with to build such a solution. It was a large-scale dashboard and alert solution. In the next slide, we will see the exact spec for this scenario. This company had already a working solution with more than 1,000 users, collecting 34 million unique customer metrics per hour. By 34 unique customer metrics, it means that each metric you can get it for every 10 seconds here. So it's a lot of data. They kept the data for 15 months. They built more than 2,000 dashboards on top of it, and in addition to that, had a lot of alerts that were running constantly on top of this data to detect anomaly detection. So what we did was to bring this data over to ADX. In the next slide is talking about the acceptance testing that we had. We had an app, of course, a testing app that was simulating 100 concurrent users, 7 different dashboards with 3 different time span. All of them are auto-refreshing every 10 seconds, at least 6 tiles per dashboard. And they wanted all of those dashboards to load with less than 5 seconds. Everything has to be super responsive. And the data should be fresh of less than 2 minutes from when it was created by the different applications. Okay, so let's move, Henning. So let's talk about the set of features that we created. In the next slide, we have a list of features. I'll go through them as fast as I can in the next 25 minutes. And if anyone here has played with Cousteau or knows Cousteau, they probably heard about those features. If not, I'm happy to introduce them. So let's start with Materialized Views, which is the next slide. And Materialized Views has essentially 3 scenarios. It's for downsampling. It's that means that if you want to aggregate stuff, let's say that you get things with a granularity of 10 seconds, and you want to aggregate it for half an hour or a day, whatever is your aggregation method that you're interested in. There is no point to do that while the user is sitting in front of the dashboard. You want to do that all the time in the background. So when the user is looking at the downsampling data, the queries are returning very fast. The second scenario is to get the last entity by the update time. So the scenario is that something is sending all the time some update, a machine configuration or something like that. And you only care about the last thing, you know, how much fuel do I have in my car, something like that. So we have in Cousteau, we have a really nice function in the summarize operator. It's called argmax. It allows us to easily get the last record by any aggregation group. It can be by the vehicle ID, by the metric, by whatever else that you care about. And you don't want to do that when the user, again, is looking at the dashboard. You want to do that in the background. And the last one is the deduplication. The deduplication, sometimes customers have issues in the pipeline. Data is duplicated, and they said, we don't want any duplication in the database. So there is another function in the aggregation function in the summarize called take any. Take any essentially says, I want to take any star, is essentially saying, I want to take the row, the entire row for each of the keys that I'm providing. And as long as the keys are the same, well, let's say, for example, if you have an ID for each line or something like that, I don't care which one it is. So the materialized view only keeps one of them if you have more than one. Okay, let's go to the next slide. So why would you use Materialized View? So we talked about the performance enhancement. It's always fresh, so that means that the data is always correct. So even though you get this amazing performance improvement, you don't lose anything essentially, except from a CPU that is working in the background to calculate all the time the view. And overall, if it's used correctly, it can reduce the cost of the cluster, because the amount of CPU invested in calculating the views is less than the amount of CPUs, or you save more CPU from the users that are using the applications, that are running the dashboards, etc. And it's a fully managed solution, so defining a materialized view is super easy. So Henning, I'm going to try now to share my screen for the demo. Okay, so let me just show the second scenario for materialized views, which is show me the last record. So the scenario that I'm showing is we have a cluster in our production cluster table in our production cluster called dim clusters. This table is essentially collecting the state of each of the Custo clusters in the entire deployment every minute or so. So for example, my cluster, his name is Avner Custo, and I'm going to project those 4 columns and take 1,000. And you can see that there is 1,000 different reads coming from the cluster. When the query will come back, let's see. Let's see again. Let me try. Okay, here it is. So we can see that there is 1,000 reads. You know, it's every minute or so something is going to send this notification, and you can see how many machines I have on my cluster and whatever configuration. But if I want I really care to see what is the current state. The history is not that interesting. So to get the current state, I can run this query, which will return me the last read, which was at today at 5:38 UTC. Okay, so I get this, and now what I'm going to do is I'm going to do a nice feature here that will focus on the query statistics. So it will show how long it takes to run this query, and it will go directly there, and you can see that the query time was 625 milliseconds, and the CPU was 15 seconds. Now let's look at the materialized view that we created. The materialized view is actually doing exactly the same as in the query. It does some calculation, and then in the end it says summarize argmax by source equal the cluster. Okay, so it's exactly the same query as it was run here, but now I can go to the materialized view. I can use it as a table, but I can also use it as through a function that essentially says I only want to create a materialized part. Why? Because materialized view, to give you the freshest result, it takes a delta and the materialized part and it merges it together, which is a bit of expensive. Still cheaper than doing the whole thing, but a bit more expensive than just go for the materialized part. And since I know that nothing really changes in the cluster any minute or something like that, I don't mind that it's a bit behind. So I'm going to use the materialized view function. That means that I'm only going to the materialized part, and I'm going to query from my function, and I'm going this time to query on the query statistics, because it's the same results. And you can see that it takes, from the CPU perspective, it's almost 14 times less resources on the cluster, right? So that's the point with the materialized view. Okay, so getting ahead to the next feature, which is leaders and followers. So today the industry is moving to the idea of storage separated from compute. So we see that with Snowflake, we see that with BigQuery, and the modern big data implementations are now separating the storage. So it keeps the storage singular, one copy of the storage, and allows many clusters and many compute resources to work on top of them. Custo provides this functionality also. It's called leaders and followers. And the leader essentially is the cluster that is ingesting the data and answering queries and doing all the data management essentially. And then from that cluster, there can be many followers that are every 15 seconds or so looking to see the storage if something changed, because Kusto is keeping all of the data that is ingested, all of the data itself, the cluster information on storage. It wakes up every 15 seconds, says, hey, something changed. And if something changed, it brings the data over. And then everybody that goes to the follower cluster is now run queries completely isolated from the cluster that is doing the ingestion, for example, or from clusters that are doing other different workloads. The follower and cluster scenario, the follower and leader scenarios is super flexible. It allows you the different configuration of a follower can follow one leader, it can follow many leaders. A leader can also be a follower. All of the different combinations that you can think about are available with the leaders and followers. We had a team at Microsoft. We have a very popular cluster at Microsoft that many teams wants to look at the data. That cluster had 18 different follower clusters for a single database. And that was already nested multiple layers of following. So it's super flexible, super, and works really, really well. So like I said, why to use it? It's protecting the production environment. In many cases, teams are not willing to pay for other teams that are using the data. So they're telling them, go ahead, create your own follower cluster, and now you can pay for your own cluster. Okay, the follower cluster, like I said, it's very flexible. And the other thing that it allows you to do is to override the caching policy and different other policies and permissions that you can do differently than the leader. It also allows table level sharing, which I think it's a unique feature now for Kusto, and I don't think that our competitors allow this feature. Okay.
I have now.
Yes.
Question from the audience. Will there be a possibility to use the follower database from the Azure portal?
Yes. Setting it up is actually through the data share, Azure Data Share. So you actually set it up through the portal. So it does work through the portal, yes. Okay. There used to be the limitation that there is that there is some latency between the follower and the leader, obviously, because the leader is writing the data and the follower is always trying to catch up. We used to have prefetch extend settings which was defaulting to false. So that means that the cluster with the follower was seeing the data that is new data and was already making it available for query. And then some queries would have seen the metadata was already available, but the data was not cached already on the follower. And that caused some performance issues. I haven't updated the slide deck, but we actually just changed this. So now the default, if you're using Engine v3, the default is that we always pre-cache the data. That added another around half a minute, I think, latency. But it guarantees that now the queries are always super fast and most optimal performance on the followers. Okay, so now let's talk about the next feature, which is data partitioning. Data partitioning can be applied to a table, and essentially it's just a policy. So you just say, I want to partition this table for 2 columns. You can choose one column, which is a datetime, and one column, which is a string. And then what we will do, we'll take each extent and we'll break it into, the default today is 128 different extents. And then those extents will be partitioned by the datetime column and or the string column, a single string column. This significantly improves the query performance because instead of looking at the whole data, we're looking at only 128 of this data, right? So it's super can provide very nice performance improvement. Why should we use it? So first I should start by saying that it costs. Like the Materialized View, to do partitioning, first the data gets ingested, and then what the partitioning process is working in the background to break the extents into the partitioned extents. This process is like ingesting the data again, essentially. So you essentially multiply or double the expense or the CPU that you spend on ingestion. And when do you want to use it? You want to use it when most of your queries are filtering by the columns that you are partitioning by. So I want to say that first I want to say that the daytime partitioning is always happening automatically in Custo. So Custo will always partition the data based on the time of the arrival. The daytime column, you should only do that when you have something where the data is coming out of order. If you're backfilling historical data or something like that, usually by default, Custo will do the daytime partitioning as long as the data arrives at the same time that it was created. And the string partitioning, you should do it when the majority of the queries are filtering using that column. Okay. So now the camera is frozen. There's not much that I can do. Let me try to share again. So what you can see, what you can see is that usually you can get, in many cases, I should say, we've seen more than 10x of improvement in the query performance. This is at least 10x. In the demo that I prepared, and I just prepared it today, I was taking a table of 35 billion records and repartitioning that. It had 10,000 different metrics coming. I partitioned it by the counter name. So and the queries that we were doing was specific for the CPU counter. So it was collecting like disk performance and CPU and networking and whatever. I saw an improvement of 388 times in the performance. So it can be very powerful technique. Okay, so let's move quickly to the next because I'm running out of time also. So weak consistency versus query consistency. So by default, Custo provide the query consistency, a strong consistency, I mean. And that means that all the queries are going to a single node, which is also doing the ingestion. What this gives you is that your queries always get the latest data, essentially, because the same node that is finalizing the ingestion is also managing the query planning and knows exactly where the new data arrives, where the new data is located, etc. Weak consistency is essentially allows other nodes in the cluster to also answer queries. And those nodes are doing exactly what the follower is doing, just on the cluster itself. So every 15 seconds, it looks at the metadata on the admin, and it brings it over to the other nodes that are handling the queries. And as a result, there is a latency, essentially, between the different nodes that are answering the queries to the admin that can be up to 15 seconds, 30 seconds. This is, by the way, the mode of production in many products that you know. If you're using Azure Monitor, that's exactly the mode that they are in, because they are getting many queries, and they need to ensure that there is no bottleneck on the cluster from the admin perspective. They arrive to 30 seconds latency at the maximum that they can see as a consistent performance and lag, and 30 seconds is okay for their use case, right? So this is something that when you write and think about high concurrency implementation, you want the clients to use the weak consistency. To use weak consistency, essentially, it's just about adding a little flag or adding a flag in the query properties when you're sending it to the server. You can also do that by default on the dashboards of Graphana and Adx Dashboards. Okay, let's move to the next item. Query results cache. So go to the next slide. So query results cache is something that you append. It's a set statement that you append to the query, and essentially you tell Custo to keep the data in the server-side cache. The history of this feature is that we had many customers internal at Microsoft that were using the cache system. What is the name of that now? It's Redis Cache. Yes. Sorry, I'm just trying to understand why the internet is not working and remembering the name of the cache of Redis Cache. So many customers were using the Redis Cache, and they came to us with a lot of questions. How should we use Redis Cache and Custo? What should we cache over there? How to reuse the cache, etc., etc., etc. In the end, we said, okay, we will build the cache. So you don't need to use the Redis Cache. And this is a feature that essentially allows our customers to not use Redis Cache and to simplify their caching solutions on their applications. And what we do essentially is we say on every query that you send to us, tell us how long you want the cache, you want to cache it essentially. In the image that you see here, we say we want to cache the query for 5 minutes. That means that if exactly the same query text will come through, you're going to get a result from the cache over the 5 minutes. After 5 minutes, it will expire, and the next time that you send afterwards, it will re-execute and refresh the data. In Grafana, first of all, I want to say that this feature is now available in the ADX dashboard. Dani and Gabi are going to show that. And the second is that Grafana has it in a more advanced mode where they calculate the caching based on the time span of the dashboard. So if the time span filter of the dashboard is for an hour, then they will calculate a cache that will be, let's say, a minute. And if the time span is a month, they will make the cache half an hour or something like that, right? So it's fully flexible the way that they do that. In our ADX implementation dashboards, I think it's a fixed value, but essentially it's super easy to use and it's super, super powerful. Also, if you use this feature, we also have a shard level caching. So that means that even if the cache itself, the queries are not identical, you're still getting benefits of caching because you also keep the shard level query in the shard cache itself. So we provide essentially 2 layers of cache. It's also something that I think that the only database that I know that is doing that today, at least that I'm aware of, and it really helps with improving the query performance. So I really recommend using that. I should also say that you can also use the cache, the shard level caching separately with a different set statement. And for some scenarios, it's more applicable. So some scenarios, the user don't want the query to ever be cached, or the queries are always different, essentially. But they know that they can reuse the shard level results of those queries, because at the shard level, the queries are the same. So they can enjoy that. So they're using shard level caching. Okay, let's move on to the next slide. And okay, and those are the features that I wanted to talk about. So the next one is just a quick overview of the different UX stacks. So we're going to move to the next talk, which is Dani and Gabi. So I'll let them explain more about those stacks. But I want to say that all of those stacks have some ways of using the features that you've seen, whether it's weak consistency, query cache results, etc. And obviously, you can use the materialized views and partitioning and make sure that the backend provides the best performance as well when you're using those applications.
Thank you so much, Avner.
Pleasure.
Thank you so much. I see customers looking at those features, and sometimes they are like trade-off between time that needs to be invested, or compute cycles that you mentioned as a cost, and the benefit that they get from it. So where do you see the fine line between using partitioning with multiple tables, materialized views with multiple tables? Is there some guidance that you can provide?
So yes, so what we've seen, yeah, thanks. It's a great question, Henning, and it's a fine line. It's hard to tell. There is no exact guidelines about how many materialized views. We've seen customers asking us, can we do 3,000 materialized views? Or can we do 3,000 partitioning policies? And I think what you need to remember, I think the intuition that everyone should have is that those features, they are running in the background in an orchestrated manner. So if you have 3,000 materialized views, that means that there will be 3,000 processes that will, in the background, will calculate the materialized views and will do the bookkeeping of them and ensure that if something fails, we'll do the retries, etc. And at a certain point, this effort can be humongous on the cluster itself, and we see that it doesn't go that far. So the advice that we have is to minimize the usage of them to where it's really needed and where the impact is the biggest. And if there is a need for materialized views, to minimize the number of tables. For example, we have a lot of customers that are doing multi-tenant that we suggest to them that for materialized view scenarios that they should put all the data in the same table. So instead of thousands of tables and thousands of materialized views, they should have a single table, and on top of that have a single materialized view. And then when they query that, they should partition that by the tenant ID or by the customer ID, whatever the multi-tenant scenario that they have. And by then they can get the performance of a table per customer, but still, or a table per tenant, but still get enjoy the materialized view. Okay, great. Okay. So what you see on the screen is a query that is actually part of our first Custo demo. So it's a demo that we're showing that already for 7 years. It's like a wine. It only gets better with the years. And this is a table that has around 30 or something billion rows. And the demo itself is essentially trying to find some abnormality behavior in the CPU. So you can see the processor total, CPU processor time, and it's looking at the max CPU, is find the top max CPU, the top machines that had the top 3 machines with max CPU. Based on the max CPU, make a list of it, and then look at all the data for that specific day and draw that on the chart. Okay, super simple. Now, if you do a decount on the number of counter names, which is like a metric, you will get something like 10,000. So I thought to myself, this is a nice scenario for partitioning, right? Because nobody really runs a query that looks at all the different metrics that the machine, nobody does a query that combines, I don't know, network and CPU and disk performance and whatever else the metrics are. All the queries will come to this table and will say, I'm interested only in this specific counter name. So it's an ideal. So Henning, if you can do 2 things. First, say .show table type .show table BI Azure additional something with partitioned. You need to refresh your metadata. You need to refresh the cluster connection so you can see it. It's a new table. So do refresh, and it will come in the IntelliSense. Okay. So you see that there is a partition, and then say policy partition. And what I did, I took the same table and I just copied it, and then I created on a new table that is _partitioned. I created a partitioning policy that was doing 2 things. One, it was doing a timestamp partitioning, and that's the timestamp is because it's an historical data from 2015. So I wanted it to go back to where it was created, essentially. So this is the scenario where I do want to partition the data based on timestamp because the data is from 7 years ago. So I want to make it look like it was 7 years ago. And the second key is, like I said, on this counter name. Okay, so now Henning, create another vertical tab. Perfect. So now take this query that you have on the left side and move it to the right side. Okay, so now we have the same query, but in the right side now use the _partitions. So the only thing that we're changing is the _partitioned. Yeah, and run this, and you see the same picture. Okay, so it's the same thing running on both, giving the same results, and it's all good. So okay, so now don't do this. Okay, fine, do this. But I want to show everybody that there is a very neat feature. If you go to the View menu, okay, go to the View menu, and now click on the Focus on Query Statistics. It's a checkbox that you can see. Yes. So click on that one. Check it. Check it. Okay, and now run this again. Okay, so it will run the query and it should move us to the query statistic automatically. It's not checked, I see. I don't have, oh, yes, it is. Okay, perfect. Now run the second one and the same, make sure that it's focused on query statistics. Okay, perfect. So now you can see that the query time went from 1 second, 1.1 seconds to 94 milliseconds. So it's 12 times faster on clock time. And you can see that the CPU time went from 10,296 to 78. So if you type a print and calculate what is the ratio, you can see how much money, how much CPU we saved by this partitioning policy. So it's 10,296. So 132 times faster, right? Now, what is the intuition behind the 132 times faster? Is because if you go to the partitioning policy again, the partitioning policy is, the default is 128. So essentially what we are doing in the queries is instead of going to the full data, looking for the results that we need, we are just looking at 128. So it's 132 times faster, right? To do that, to show the data scanned, right?
Yep.
So if you look at the data scanned here, in this one, in the right side, no, not in the, just on the query summary. Yeah, so you see the data scan is 22 megabytes, and on the left-hand side, it's supposed to be something like in the gigabytes, 8.7 gigabytes. So the query is, it's not a magic, the query is just doing much less work, so it's super, super fast. So it's also important, I think, that you'll have the right intuition about how the performance of Custo, what is the magic behind this performance. It's not a magic, it's just query operators that are doing work. And if you know how to, you know what the bottleneck or what is where the work is doing, you can do a lot to make it much faster and simpler.
So Avner, looking at this query, what else could be what else could be optimized? Is there room for it? Now that you brought it up, now that you show the query, you can also look at it.
Yes. Well, so I think Henning is trying to say that if you use Materialize, he was trying to do, he would have failed, of course, because there is a way. If you, what Henning was trying to show is that if you use a Materialize function and you have a common queries section of the query that is being used a couple of times, you can materialize it. What does it mean? It's essentially, it's like an intermediate cache. You calculate the result of whatever is in the Materialize. Custo will write it to disk, and it will just reuse those results to execute the rest of the query. What the problem is that if there's too many results, like in this case, if you do a lookup input and count it, Henning, I think you will see that there will be, it might be, I actually don't know, but if you do a count on this.
Sorry, yeah, my fault.
So it will help if the amount of data is small, and it will not, okay, so 262,000 record, that might be a good candidate to cache. Usually we try to cache not a lot because the act of writing stuff I think here, if you use the materialize, I think it will slow things up. See? I'm not sure about it. Okay.
Last time it was 63. Okay.
63 or 93?
63.
I think Henning is going to a good direction. There is a query performance tricks, and that is documented, of course. And it would be great if everybody, look at those things and play with them and get the intuition for that. That's really super fun. I always find it super fun, and Henning as well, as you can see, and to make the queries run faster. And in Kusto, I think it's much simpler than doing that in SQL, for example. SQL, I think you need to be a real expert, SQL expert, to get to these levels. And in Kusto, I think it's there is just a few places that you can touch, and that we leave it for the user to tell us how to optimize the query.
Cool. Very nice. Very, very impressive. Okay. Now,
any questions? There was nobody. No questions.
Okay, so maybe one last question on another way of scaling out. Sometimes with customers, I get the question, listen, Henning, I want to collect all of this telemetry data, and my main purpose of my division is storing all of that data. Now, if I store all of that data, I need some CPU cycles to make it nice, to put it into the right schema, eventually do some update policies. And then over time, like more and more use cases are onboarded to the exact same cluster. So they share the same CPUs.
Right.
So this might be nice for the first or for the second use case, but over time, those use cases, they will like sum up, and eventually all of them will be some sort of a bad neighbor to each other at a certain point. Eventually, you don't know. So can you maybe provide some guidance when to use something like a workload groups versus doing a full scale out to a follower cluster?
Right. This is excellent, super excellent question. So it's a feature that I haven't talked about. So let's go back one step. So follower cluster is the best way to isolate workload and noisy neighbors and allow them to be fully isolated. There's no relationship at all. And but we also provide on the cluster level, we provide the ability to create workload groups where every query and every query essentially can be categorized to different workload groups. And those workload groups can get assignment of specific resources from the cluster. For example, concurrency. So you can say this workload group, which is doing dashboards, can have 100 concurrent features, and the data science team can have only 3 concurrent queries because their queries are heavy and they're going to impact more the neighbors. Or you can have a workload group setting that says this workload group is going to have only 10 seconds for a timeout before the query times out. And this other workload group is going to have 4 minutes because their query are longer and so forth. So you can play with those things, but the workload group does not provide really a good mechanism for the noisy neighbor problem. It does allow, it alleviates a bit the issues. It allows giving priorities. It allows keeping certain workload bounded by different parameters. As a cluster admin, I might want to bound the different workloads to by different parameters. I want to ensure that they are not consuming too many resources of the cluster, but it's still on it's not a fully bulletproof solution. But we see a great adoption, by the way, for the workload groups because it does allow many protection mechanisms for the cluster heads.
Great. Yeah, thank you so much for helping our attendees to get a deeper understanding on when to use workload groups versus when to use followers. Thank you so much, Avner. Thank you so much for spending the time with us and explaining all of these things. Dear attendees, this is super important information. You will be like very happy with Azure Data Explorer, and then you also would like to scale out your read performance by using all of these different features that Avner explained, starting from our consistency models to partitioning to materialized views, follower clusters, all of that. And I hope that you enjoyed the I hope that you in Query Cache, definitely. I hope that you enjoyed the talk. Thank you so much, Avner, for spending time with us. And by that, I would like to hand over to Dani and Gabi. Please introduce yourself and take it away. Have fun.
We'll be talking about dashboard integrations of Azure Data Explorer. We'll cover some of the solutions, the main solutions that we are working with. Maybe a short intro before we start. I'm a product manager in Azure Data Explorer team, mainly focusing around management, around monitoring and dashboard integrations. Dani, do you want to introduce yourself? And then we can get started.
Yeah, so my name is Danny Hotter. I'm also a product manager in the same team. And my main areas of focus is integration with Power BI. And also I work on internal BI for the team, mainly using, again, Power BI for this internal BI.
Great. So moving forward, today with Azure Data Explorer, we have a few visualization integrations. First of all, we have the built-in ADX dashboards. We'll cover that. We'll tell you what you can do with that and in which scenarios it's like best to use it. We also have native connectors. We have a native connector to Power BI, to Grafana, Seek, Redis, and we have a partial connector to Kibana, which supports some of the capabilities in Kibana. And in addition, we support the ODBC and JDBC connectors that allows basically connecting to any SQL using visualization service like Tableau, Qlik, Sisense, and others.
We should also mention the TDS endpoint. I think it should be here in this slide because just to mention that ADX can actually present itself as a SQL Azure database. So any tool in any scenario that can use SQL Azure can also use Cousteau and send the SQL commands, and we support the SQL commands. And one example for that is paginated reports that sometimes actually come very handy.
Great, thanks. By the way, Henning, can people ask questions? Is it
of course?
Okay.
So people will be able to ask questions in the chat. We're going to answer them. And if I see something that is that I should like tell you, then I will immediately
great.
Unmute.
Excellent. Okay, so we'll cover Power BI more in details, but in essence, it's one of the best tools out there, maybe even the best there is. It has tons of features and it's relatively easy to use. We have a native connector that allows us to use both import and direct query modes. And Dani will go into that with more details. One of the recent additions is making M-dynamic parameters GA, which happened around a month ago. Next one is Grafana. So Grafana, if you're not familiar with it, it's an open source solution. It can you can either build it yourself or use the hosted Grafana. Today, there is also an offering in Azure, which is called Azure Managed Grafana. It's usually used for time series use cases. It's for real-time and operational scenarios. And again, we have a connector that we are building together with the Grafana team, which focuses on near real-time use cases. We have there a query builder that allows you to create visuals very easily without writing KQL. So that's another benefit, and I'll show that in the demo a bit later. Moving forward, we have Adx Dashboards, which is part of our web UI client. That includes a query experience and a dashboards experience, and also an area for creating or ingesting data. And probably, I guess that Avner also mentioned the free cluster, which is also part of the web UI. So there we have a native experience that allows you to move between dashboards and query relatively easy. We have a very deep integration with parameters, which are powering the dashboards, and I'll show you some of the features that are driven by parameters. And we'll cover some of the additional capabilities. Also, I'll demo this tool a bit later. In general, probably some of you are asking, when should we use each solution? And basically, there are a few different reasons for selecting one opposed to the other. So first of all, if your organization today is already using one of the tools, then you'll probably want to continue using that same tool. So that's one main motivation for customers to using one of the dashboard integrations that we have today. If like you need the breadth of features that Power BI has, then this is something that probably you won't be able to get either in ADX Dashboards or in Grafana. Power BI really has tons of features, and I think even Danny don't necessarily know all of them. I'm not sure, but maybe. So Power BI really has a lot of features that you can use, a lot of visualizations, custom visualizations, a very mature embedded experience, and much more. If you are, if you need to run more like complicated queries on top of very big data, then probably from performance point of view, you'll get better results with ADX Dashboards and Grafana, mainly since they are using KQL natively, and they're not doing any translations like Power BI is doing. So there are a lot of optimizations that can be done in Power BI in order to improve the performance significantly, and Danny will show you some of them. But probably if you are on a really high scale solution with very complicated queries, then probably either ADX Dashboards or Grafana would provide you with a more performant experience. So that's in a nutshell like the different considerations for selecting each one of the solutions. So I don't know if there are any questions up to now. If not, we can move to Danny's demo of Power BI.
Go for it.
So hello everyone, and we'll go through some of the topics that you need to understand about using Power BI. So I'm going to do a quick demo over data that maybe you saw before in this series, the GitHub data. That is a large, relatively large data set, not as large as the one that Avner was using, but still pretty large. And you can see how the performance of ADX actually surfaces through Power BI. Gabi mentioned that there is an overhead of translations. It's not that simple. So there is a fixed overhead for every query that you send from Power BI. Power BI takes some time to prepare it and send it and so on. And it's an overhead that is measured in a few hundreds of milliseconds per query. But if you run a query that runs on top of a lot of data, it's going to the backend, run in the backend, and sends aggregated data, summarized data back to Power BI. So it should go very fast. And also now, if I start using, so I'm in an empty Power BI, and I will go to get data, and now it's collecting all the data sources. So one of the advantages of Power BI that it actually supports tons of data sources. So a report doesn't have to be necessarily just using native ADX. It can mix ADX and SQL and an Excel file and a CSV file, and some of it can be imported and some other parts can be in direct query. So there's a lot of combinations you can do, and it doesn't have to be all coming from Cousteau. So I'm looking for the Cousteau connector. I'm writing part of it. Here it is, and I'm connecting. Now I'm going to connect to this cluster. And I need not to forget to scroll down to where I see here the choice between import and direct query. In between, so I could just, that's what I will do. I will just connect to the cluster and continue in the navigation. But I can also provide here the database, and I can also provide here a full-blown query that I copied from somewhere else. Let's say I use Cousteau Explorer or Cousteau Web Explorer, and I already have a query that is, I tested it and it's good and it's maybe even complex, so they don't want to create it here. I can copy it here. I personally don't like so much this option. I always recommend to people, if they have complex logic that they want to use from Power BI, to create functions in Cousteau and call the functions from here. And I will show you the experience of using a function and even providing parameters to the function. And I find this to be the best option to keep all the logic in ADX. Then you can test it, then you can save it. And also, if you have multiple reports that are using the same logic, it has to exist only once in this function, not be copied over to all of your reports. Some other things you can do here is to set some parameters. By default, if you import data into Power BI, the default is that you can import not more than 500,000 rows. You can increase that. You can just say here, for example, set truncation, disable set truncation altogether, say here true, and you will not be limited at all. I would not recommend to try to import large amounts of data, but it's possible. And also you can have here other settings like using cache, using consistency levels and so on. So every settings that you want to use, you can use it from here. We don't have this smart logic of adjusting the cache automatically, but you can put the cache here. So I'm selecting here direct query and I go forward. Now it's actually discovering the content of this cluster, and I'm going to use from GitHub, I'm going to use the table that is getting all the events in streaming mode, which is called event from live stream. And I get a preview of the data. You see that there are 3 columns here, which are set here, shown here as records, because those 3, we'll see them in a moment. They are actually JSONs. And so Power BI recognized them as something that in Power BI terminology, it's called a record. So now I see the preview of 1,000 rows out of this table. And you see here, there's other 3. And for now, I will not do anything with them. So I will just select a subset, a small subset of the columns, actually just the type and the date, and remove all other columns. So I'm doing regular Power BI stuff. I'm doing regular Power Query. Actually, I'm in Power Query. In the editor, I'm doing transformations. For example, I can go here and rename this column, and I can go and change the type from what it is now, daytime time zone, to just daytime. And I can add new columns. And everything I do here is actually translated to KQL. If I go to the last step or any other step before, and I do right click here and view native query, I see the KQL that was generated by the connector based on the transformation steps that I did so far. It was not a lot, but it can get more complex. So let's say I'm just doing a custom column, and I will name it foo, and it will take the type and concatenate the word type to it. I don't know, not very smart, but still some calculation. So this calculation is also now translated to, you see here, foo is using this strcut function to concatenate the type with the word type and so on. and go and delete it. So once I'm happy with what I did, I can just close this and go to my report. Now it's actually going to load, but not really load, because this is direct query. It doesn't load anything. It just prepares the query, and I will, in a few seconds, I will see the query ready to start doing my report. All right, so I have here the table, and it just have 2 columns, and I can start, for example, I can do a table, drag the column type to the table. Now, actually, there is a query behind the scenes sent by Power BI to get all distinct values of type from this table, which happens to have 2.6 billion rows. Now I will create a measure, so I can create measures the same way I will create measures with Power BI, and the measure syntax will also be translated to KQL. There are some limitations. You might get, if you really try to go crazy with your measures, you might get a message that says that what you did cannot be translated or cannot be folded. The term is folded to the native syntax, and you have to somehow do it differently. But here it's a simple one. It just counts rows of this table. And I will just format it with a comma. It will be readable. And now I can just drag the measure to the table. Now it goes and sends, and I will sort it. So we'll see the bigger ones. So we see that there are 2.6 billion rows in the table. The one event type with more than anything else is push events, and it goes down. And there are even 16 rows with an empty type. Now what I can do, I can also have some filtering on top. So I will drag the time to its own visual and make this visual into a slicer. And in the slicer, I have a choice of different ways of just. I can just do a between with this slider, but I will do something else. I will do a relative. Because this data is streaming and it's kind of close to real time, we just have a lag of a few minutes. I can do stuff like show me just the data that came in the last 3 days. And now a query was sent, the results came back, so now we are only at 9 million rows, which is what was done in the last few days, 3 days. I can also do a relative time because, again, this is, so I can say, show me the data from the last 15 minutes. So not a lot, because there's also the delay, or I can say, so I can go to hours and so on. And every time I do this kind of an interaction, a query will be sent to Power BI. The aggregated results will come back, and you can see that it all works pretty well. Any questions at this point? Any?
Not related to this. Not related.
All right,
to this.
all right.
Thank you.
So I want to move out to the next. So I will just jump a little bit to the Gusto Web Explorer, and I want to show you a few things here, because one of the important things to think about when you use Power BI and with the ADX data is about should I use multiple tables? Should I use one big table? And if I use multiple tables, how would I join them? What kind of relationships will I have? This is the source for a lot of the performance issues that people feel when they start using multiple tables and joins. And there are ways to work around it, but we need to be aware. Not the common things that if you have experience with Power BI and you've been doing things maybe for years, and you were taught that the best approach is to use the star schema architecture with a fact table and dimensions which are related to it. It's not the best option always with Power BI, and we'll see. So now I'm actually switched to the help cluster that every one of you can actually access and do exactly what I'm doing now, because the help cluster is open for everyone. And in here, I have a database that I copied from the Contoso and data warehouse, which is a very famous demo data warehouse coming with SQL and analysis services and Power BI and so on. So a lot of demos are based on this. And I have here the data basically in two forms. I have it in one table that is called sales table, which have all the information that originally was coming from the fact table, which with sales, plus the products table, plus the customer table. So everything in one table. I ingested it already in this form. And there's different ways to achieve this. Could be update policies, could be that you actually combine it before, but anyhow, this is the end result, that you have one big table. The other form is that I have a narrow table with just a few columns, but in order to enrich it with data from the customers and products table, I will need to join it. So if we, for example, do here, before we go back to Power BI, if I go here, sales table, summarize, let's say sales equals sum of sales amount by country and color, which is, I choose this two because one of them is coming from originally from the customers table and one of them is coming from the product table. So I see that this was using 3 megabytes maximum of memory, took execution point 14, CPU very, very light. Now, if I want to use the other table, I will have to join. And if I will do the joins, the kind of joins that Power BI will do, it will be something like sales fact, join customers, and let's say let's say inner customers on customer key, and I will join kind equals inner to products on product key. And now I will do the same. Now that I have all the information, basically the same way it was there. Actually, the country has a different name. Yeah, okay. So now I'm doing something which is supposed to be similar to what I just did. And now we see that the amount of memory used is much, 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 much bigger. Just to remind you, here it was 3 megabytes. Here is 377 megabytes. CPU is higher. Everything is higher, significantly higher. This is why. This is because Power BI doesn't like this kind of join. In Power BI, you should always present the small table first and the large table second. And so if I want to do the best join I can do, I will actually replace the join with another verb called lookup, which will actually do the reversing for me. So if I do lookup, it means that this is actually something like a fact table, and I will look up it with 2 dimensions. So this way, it also uses a hint called broadcast. Anyhow, this is the best way you can do this kind of join. And let's see by how much I can improve it using this method. You see that now it's using 12 megabytes. It's not as good as just having everything pre-joined, but it's pretty good. So avoiding this the first kind of joins that I was doing is very important if you want, because here it was just taking more CPU. But eventually, if the tables will come bigger, it will not be enough memory in the world to do this. You will just get errors out of memory if you try to do joins of large tables with small tables. in the regular way. So what can you do? I'm just opening a new Power BI because I'm switching to a different area altogether. Maybe not the smartest thing to do because, oh. So now I'm going to use this data from help. So how can I treat this scenario with multiple tables? So if I'm using the one table, there's no point in showing it. It's just using everything is in one table, and I can do whatever I want. I can do slides, so I can do charts on top of everything, and everything will be fast coming from this single table. But what if I don't have a single table for different reasons? It's difficult for me to actually get it to this state, and I still want to use multiple tables. So there are basically two approaches. Help, direct query. The first approach is I will bring the three tables, the fact, sales fact, together with the two dimensions. So I want this, I want this, I want this. And I don't need to do any transformation, so I can just click load and pull everything in. And now I will create three queries. I'm going pretty fast, but there's documentation and articles that describe this and describe the different options and the optimizations. And if you actually encounter any issues, you can find me, and I would be happy to help in any Power BI plus ADX implementation. Okay, now if I'm going to look at the tables, if I want to do anything with these tables, I need to create relationships. Now here there's a little difference. If I drag here and connect those two, you'll see some strange behavior that here now it says many to one single, and after a few seconds it changed its mind and it says, oh no, actually it's many to many with both. The reason for that is actually that Power BI tries to see if the data is unique, or the key is unique on the product side, and in order to do that, it compares the number of rows to the number of unique values in product key, which is identical, but because distinct count in Power BI in ADX, distinct count is an estimate. It has some margin of error in order to make it to be able to do it fast. It gets different results, and it kind of confused. But I don't mind. If you were taught never to use many to many, don't worry about it. With Power BI, with ADX, it's fine. Only you have to set the direction of the relationship, and that's it. And now we have a relationship, and we can do the same for the other one, but for the sake of time, I will just skip it. Now we have two tables with a relationship, and products can filter fact. Now, when I will use it, and I'm not going to go through because I have another topic I want to show you. So when I'm going to use this data in my report, and I will do, for example, I don't know, I will just take a table for colors, and I will just I connect with product, yes. So I take all the product colors and I drag the sales amount to here. So what actually I forced now, there was a join, the statement with join sent to the server. The join is the slow version of the join, which here it wasn't too bad, but still it will be pretty bad eventually, and we want to avoid it. The simplest way to avoid it is actually to say that we are going to use a mix mode. When the dimensions, like the product, I will change it to be in import mode. So now we have a fact in coming direct query from ADX. Every time I query, it will be fresh data, and the dimension will be imported, and I will have to refresh it periodically, maybe once a day, maybe more. But usually, this kind of tables are not that as dynamic as the actual events that are happening all the time. And now the query was different. There was no join because there's nothing to join with, because the data is partly inside Power BI. So the query was different, and we avoid the join. We pay a little price in the kind of query we send, but it's fine as long as the dimension is not huge. I've been working with customers who have had millions of, let's say, products. And in this case, this method of mixing import and direct query doesn't work. Another option that you could do is actually making it look like one table by just creating a proper lookup, let's say, joining with lookup or joining the right way with broadcast and everything, putting it in a query, let's say in a function, and calling the thing as if it was one table. So for Power BI, it will be one table. On the back end, it will still have joins, but the joins will be optimal, like I showed you. And this is another option to actually get over it. The last thing I wanted to show you is how to use a function. So again, I will switch to, so I have a simple function here. You see it, it's called summarize with params, and it gets two parameters. One is the country, one is the color. And what it does, it calls the sales table. It filters it by a single country and a single color. It's a very simple case. It could be, I can create it so that it will be not a single list, but actually multiple values, but just to show it the simplest way. And then I'm summarizing after I filter. And in some cases, this could make a lot of difference, because if I just use the regular way, if you think about the regular way that Power BI will work, if we switch back to Power BI, if I create this kind of visual, there is the original query, which could be just a simple table with some modifications, like we saw some transformations. And then Power BI adds to it other parts. It can add a slice, so filter the results by slicer. It will definitely add summarize of the results, because here it's a summary by color, so it needs to summarize. So part of the data, the query will come from what we saw in Power Query, and then additional parts will be added to it at the end to do additional filtering and to do summarize. Now, this order of things is not always optimal, because sometimes you need to filter before you summarize, or you need to do something in a specific order, and you cannot do something dynamic based on the user's activity in Power BI without using a special feature that I will show you. But first, let's call the function that I showed you. So instead of starting from get data, I will start from recent sources, which is the health cluster. So I'm just skipping the connection and so on. And here I see, besides the tables, I also see the functions we see with special icons. And I have this sales with params. There is some magic here that actually recognizes that this is something that needs to get, oh, no, not this one. Sorry. I have to refresh it and do it again. It's not this function. This function is something else. Let me just go back. What was it? Summarize with params. Where is it? Right. Why don't I see summarize?
Did you create it?
Sorry?
Did you create it? Like you have the script, but did you?
Let's make sure. Oh, I did not. Thank you. I just wrote it there's a few minutes ago. Okay, so it recognizes that this is a function that expects two parameters. So I can provide two values for now. Let's say I want to use France, and I want to use color red, and I would apply, and it actually will call the function, giving it these two parameters. And here I get the results. I can go into transform data, Now it asked me because I started from recent sources, now it's the good time to ask me if I want direct query. I said, yes, I want direct query. And I go into the editor with this data and with this query. And what you see here is a statement that is actually calling the function. It's calling the function with these two parameters, but I don't want the parameters to stay fixed. I want them to be dynamic. I want to be able to provide the values that the user will select the values from a list of countries or colors or both. And this selection will actually flow into here. And this is the feature that Gabi mentioned, the dynamic parameters. So the way to do it is, I will do one just because I don't have a lot of time. I'm going to a show, so that's why I'm a little stressed here. So let's say country param, let's call it this parameter. This is a normal Power Query parameter, so far at this point. So this is something that is, and I will give it a value, let's say Canada. Now we have a parameter which has a fixed value of Canada. I'm going back to my query, and I will say, instead of just fix France, I will say use the country param. And I will leave the other one. You see the states here, you see the class, and I will leave the red as fixed, but the same thing I can do here. Okay, one more thing I want to do is actually I want to use this products table, but now I want to use it in a special use. I want to create from it a list of countries. So I'm going to reuse this one not this one, this one. I'm going to use this one just to create for me a list of countries. So I'm going to the country column, removing all other columns. I'm going to remove rows, remove duplicates, and all this is translated to KQL, no problem at all. So you see here, although this is actually going to be an import, but still it's going to be imported in a very efficient query, giving me the list of countries. And I'm happy with what I did, and I'm closing from here. So now I have a query that expects to get a parameter, which is a country, and I want to provide the user with, I'm going to build another. So next step I have to do, I have this customers table, and I have the region country name column, and I need to go here, go to the properties, click on advanced, going to the bottom here, and say that I want to connect this column to the country param. They need to be the same type, and they are, so it's fine. Go back to the report. So first thing I will do is do a slicer. Let me just first call it a slicer, because otherwise it will create a map. Okay, so I have here a list of countries, and now I can use my query, this one with a function. So I'm going to use the sales. By default, it's going to create me a bar chart, and I will just use it by, let's say, by class. So it will just show a few charts, and now I can switch between the countries. Every time I switch to a country, it actually injects the value for this country into the queries through the parameter, queries the data, and bring me back the result. And it does it. There's no relationship between this table and the sales table. It's just because of this combination of the m-dynamic parameter. There are some cases in which this is essential. Without it, you just can't achieve what you want to do. Here it was kind of simplistic, but And of course, also I can make it so that you could select multiple countries and not just one. But here I just wanted to show you the simple use of this feature. That's all I wanted to show. Any questions?
Thank you so much. Thank you so much.
All right. Enjoy the rest of it. Bye.
Bye-bye. Can you see my screen?
Yes. Great.
So as I said before, I'll be covering both Grafana experience, giving some examples, and ADX dashboards, give you the highlights. How much time do I have, Henning? Until what time?
Probably like 10 minutes.
Okay, so I'll go through it really quickly. Okay, so this is Grafana. Here we have an empty dashboard, and I'm creating the first panel. So I'll start from here. I'll add a new panel. And sorry, my laptop for some reason seems to be really slow this evening, so it might take some time. So here in Grafana, I need to select a data source. I need to configure a data source connecting me to an Azure Data Explorer database ahead of time. So I'm using the same database that Danny showed with the GitHub data. I'm selecting the GitHub Demo 11 cluster, and I'm using GitHub database, and then I can select one of the tables in that database. Everything here is auto-populated. This is the query builder experience I mentioned before. So I'll be selecting the events from live stream table. And once I'm selecting it, basically I have an experience that allows me to select filters, to do all kinds of aggregations, and group by different columns. So I'll create a simple filter. I'll filter by the type of the event. So as soon as I start typing, I'm getting from the actual table the column names. Everything here is auto-populated. I can also go and start typing in a value from that column, and I'm getting the actual value that I can use. So here I'm filtering only to events that are from push event type. I can add an aggregation. Let's say that I'll take a count aggregation and count all of the events that are of type push event for a specific period. So I'll do the grouping by the date time column, and I'm starting to type the name of the column and that's created at. And I can use the auto binning as initial step. So once I run the query, I'll get all of the data for the last 6 hours related to all of the events that are of push event. And you see that I didn't have to write any KQL code. It was super simple, drop downs and auto-populated controls, and you have something coming from the actual data. In parallel, you can see that we are generating a KQL query down here. So it can serve you both for education to see how a query is being built, and also you can use it and move to editing the query itself if you want to go and do more advanced stuff than the query builder can do. Before we go there, let me show you another nice capability of the Grafana connector. So basically I duplicated the query, and I have now 2 queries that are running the same KQL code. And for the second query, I can say that I want to do a week-over-week comparison. So once I run it, I am basically running the same query, but the connector itself is shifting the time by 7 days to the previous week. And I can see a comparison of my events from this week in the green and from the previous week in the yellow. And that's very useful in many cases where you need to do a week over a week, day over a day, and similar use cases. Let's get rid of that. Let's go back to the original query. And now I'll show you how I can go and edit the KQL. So I go and basically go into the raw mode. And now I can manipulate the query itself. So let's say that I'll remove the filter. I don't want to get only the push event types. And I'll do the aggregation by the binning of the time and also by the type. So that basically means that I'll be getting a series for each event type. So you see here that now I have multiple series. I have actually 15 series for the entire set of event types that I have in my data. So that's that's super easy to go into the query and edit it and do more like granular and add more capabilities that are not part of the query builder. Let me now show you a full dashboard. Here we have an IoT sample dashboard that basically brings you data that around temperatures and humidity and battery status of different devices. You have here filters, so you can add and remove devices. Like you can add different ones, and you can do filtering. And you see that everything is being populated accordingly, super quick. And for time series use cases, it's really it's a really useful tool to get the data that you need. If there are any questions on Grafana, then let me know any. If not, I'm moving forward to ADX Dashboard.
Please move forward.
Okay. So this is ADX Dashboard, and again, connecting to the same cluster, same database, showing GitHub data. So here you can see that I have different types of tiles. I have filters here on the top, so I can do all kind of filtering. So here, for example, I can also select different event types. Once I select them, then the data is being filtered accordingly. I can filter by time and do some more. I can also use cross filter, which is basically allowing me to select a data point. For example, I'll select a created event, and that filters my entire dashboard. I can also go and drag and drop some points here and filter the data only for this time range, basically. So I have here multiple capabilities in order to filter the data. In addition, I have a drill through capability, just like in Power BI. And if you take a look here, you can see that I have two pages in the dashboard. I have the primary page that you're currently seeing, and I have another page with one visual that I'm using as a drill target. So if I'm coming here to this visual and I'm selecting drill through to the drill target page, and basically it takes the created event value and puts it here on the filter and filters the other page according to the same, like the values that I selected in the data points. And if I want to go back, I can easily do that and remove the filter, just like you can do with Power BI. Maybe I'll show you one last thing before we close this piece. The concept or the object that supports all of the filtering and cross filtering and drill throughs is called parameter. So we define the parameters here. We can create a list of parameters. I've been using the event type parameters during this demo, so let's take a look at that parameter. So you can define different properties. For example, you can define whether it's a multiple selection, single selection, free text, or time range type of a parameter. You can define the name that we're going to use in the query. I'll show you later on how to use it. You need to define the data type, on which pages you want to use this parameter as a filter. You can use a query to populate the filter with values. So here, for example, I'm using a query that returns all of the values from the actual data set. So you see here the values that I'm using. For some reason, the query itself is not being shown here. Maybe it's also related to the slowness I'm experiencing here. So you need to believe me that if everything was working here well, you would see here a KQL query. And I can select the value column I want to present and default value and so on and so forth. So once I have a parameter, once I define the parameter, I can go to a query. Let's close this one. I can go to a query. Let's say, for example, that I'm going to edit this query. And again, I have the same issue with the query not being shown. Let me refresh this page. So basically, each tile today is being populated using a query, a KQL query. So let's try that again. And if it won't work, you can see that in the documentation. Okay, great. Okay, so now you can see that I have here a KQL query. And if I want to use the event type parameter, basically what I need to do is to add it to the query itself. So here, for example, you see that I have all of the parameters that I've defined to use in this specific page. So the event type parameter is disabled because I didn't use it in the query yet. So once I add a where statement, and I'll select a parameter, and I'll select an in command because I have a multiple selection parameter, and then I'm using the parameter name, the variable name that I showed you in the previous page. And once I am selecting it, I can already come here and start selecting stuff, and it will basically run and modify the results here according to the selections that I've made. So that's the way to add a parameter, and there are some more tweaks that you can use, but let's settle for this for now. Another option, another capability that you can use is being able to export dashboards to a file, to a JSON file, and then you can edit them offline and import them back in order to replace the dashboard or to create a dashboard, a new dashboard using that file as kind of a template. I'll stop here since we're close to the end of the time.
Yeah, thank you so much, Gabi, for this session. May I ask you more like an open-ended question? Like you showed in this session, Power BI, Grafana. You also showed our own Gusto dashboards. Can you provide some guidance on when to use what?
Yeah, so
with technology.
Yeah, as I said before, there are different considerations for making that choice. So if you're using today Power BI widely in your organization, then probably you'll continue using Power BI, and it makes a lot of sense. If you're not, let's assume that you are an organization that is not using anything today. So the main considerations to take are, first of all, do you need, ADX Dashboards has significantly less or lower amount of features compared to Power BI. So if there are any Power BI features, specific features that you need, and ADX Dashboards don't have them, and Grafana don't have it also, then probably we will recommend using Power BI. So the main reason for using Power BI is the breadth of features, data sources that it supports, visual types that it supports. I think it's probably the BI service with the biggest set of options that you can find today. If you're not if you don't need that and you're more focused on the operational use case, the time series use case, then probably you'll get a better fit using either Grafana or ADX Dashboards. Grafana is a more mature solution. It's been out there for many years. It supports also quite a big list of data sources, not as big as Power BI, but a significant list of data sources. So if you need additional data sources on top of ADX Gusto, then probably Grafana would be better for that scenario. But basically, as I said, either Grafana or ADX Dashboards has a better fit for use cases where you need really large amounts of data, complicated queries, and you need to have you need to control both the load on the cluster and get better performance, dashboard rendering performance. So in those cases, I'll probably go with ADX Dashboards or Grafana. There are, of course, additional considerations like pricing. So Power BI is a paid service. Grafana is either an open source, or you can pay for the hosted Grafana, or I use the managed Grafana in Azure. ADX is totally free, so there are multiple considerations to take here.
Maybe one last question, Gabi. One last question. In our session yesterday, I was also showing dashboards, and I did a full-blown hands-on lab. At the point in time where the attendees saw the dashboards and its capabilities, one of the first questions that came up is, what about embedding those dashboards? Is this something that we're going to support?
You're talking about ADX dashboards?
Correct.
Okay, so that's a great question. As they say, we've been working on iframe embedding of our dashboard, and actually we're starting this week private preview with the first customer. So I'm assuming that iframe embedding would probably be available in the next 2 to 4 weeks for everybody to use.
Wow, that's really great news. Thank you so much, Gabi, for that. I hope you don't mind if I take over. Is there anything else that you still want to share? Or
no,
okay.
Just I hope that you enjoyed.
I enjoyed it very, very much, and I hope that our attendees enjoyed it as well. And now, actually, we can call it a day. That was our Level 300 workshop. Thank you so much to all of the presenters. Also, thank you to everyone who's supporting in the background, answering questions. Jill, VP, Brad, yesterday. Thank you so much for all of your help. I hope it was useful for you. The slide that I'm showing here is just some general recommendations to look for, product guidelines, social and community links for Twitter and LinkedIn. So probably you find us everywhere. Also our free online courses and some hands-on sessions, so please check it out. But again, most asked questions in this workshop, yes, you get the recording. Yes, you get a nice content package. We are going to deliver all of that to you eventually. And by that, I would like to say thank you, and have a great rest of the day. And I hope you enjoyed the workshop. Cheers. Bye-bye.